Okay, so the next part, so I wanted to take some extra time on that to make sure we went through everything. The next section would be section 46. Has anyone gone through, well, let me ask you guys, has everyone gone through section 45 yet? Okay, that's okay. Like I see a lot of head shakes back and stuff like that, and that's all right. I kind of figured you guys are all working really hard on that project, right? So no worries in that. Plus, we got a little bit of break, so you can kind of catch up and stuff as you need. But this is where I see we have about 15 minutes left of study group. So I'm not going to try to push all of it through like within 15 minutes because I don't think that would give it justice. What we'll do is that I'll go through at least part of it, and then was it next time, which is Tuesday, we'll go more into the optimizations before moving on to this part. That way we can make sure you have time to, like, I don't want to just basically just run through it all really quickly and then you not have any information, like basically try to squeeze it all in. Okay. So, all right. Okay. So now we're going to move on to parts of section 47, which will be for overfitting and then optimizations. So we're going to talk about some overfitting parts, basically how do we avoid overfitting neural networks? Because as we get things that are more and more complicated, right, we'll basically have issues with overfitting. The more complicated the data set is, or not data set, more complicated the model is, the more danger we have overfitting on top of that model, right? And we can see this before with other machine learning algorithms. So a really quick thing, just remember you should always do your train validation tests. I won't go over this part because I think hopefully I kind of really dug it into you guys in your head and say, hey, you should have your training data set and then your testing data set, which is like a holdout, which basically means like you don't touch it until you're done with all your training. And then we have the validation set, which is kind of like a little practice test. It says, we don't use it for training directly, but we use it to basically see how well the training has been doing. Okay. Note that validation tests and validation sets and test data sets, right? So like we have our test data set, our validation data set, they should come from the same distribution. So they should look very similar to each other. And the reason why for that, hopefully that makes sense, is that you want to make sure your practice test looks like the real deal. If it doesn't look like the real deal, you're going to mess up on some things and not realize it until basically at the very end. This is a real issue where as data sets come through, our data evolves essentially. Like, let's say you are making predictions for, predicting houses for like, people are buying houses in the 1950s or something like that. And you're making, a model that makes that prediction. Well, in 20 years later, your model is not going to perform in the same way because things have changed. So you'd want to make sure you kind of keep feeding in and making those test sets and the validation sets match well for what will be put out in production. Okay, so just kind of a quick reminder. All right, so model complexity graph, we talked about this before too, so I'm not gonna harp on it too long, but we've seen like basically your training error should basically get smaller and smaller as the complexity goes further. Note that complexity for neural networks can be simply just being you're training it longer, more epochs. And then as your validation error kind of goes, will go smaller and smaller and smaller too. But what will likely happen is at a certain point, it basically starts overfitting and you can start seeing that. And it's kind of like elbow plot going forward. So note that basically there's two parts in here. If we want to make sure we don't underfit, we don't want to stop it too early. We want to make sure it's complex enough, but we don't want to overfit. And we can identify overfitting by saying, hey, our training error, or sorry, our validation error is starting to spike up again. Because our training error will always go smaller and smaller and smaller, which makes sense because it's gradient descent, right? It's trying to find the most optimal way for the training error. But our validation error basically is that extra practice test to make sure we're training on the right stuff. Okay. So this is where the curriculum talks about something called early stopping. And early stopping is a really great thing. I don't quite agree with how the curriculum talks about early stopping. So one thing they say in the curriculum, if you go through section 46, is that they say, all right, you do this plot, which is what you should do. And you see, oh, for example, 100 epochs, right? And say, okay, 100 epochs is really our sweet spot, right? So we're going to retrain the whole thing over 100 epochs. Couple of issues with that. One, you just trained it. Like, why do you have to train it again? Wouldn't it be nice if we just could go back in time and pick this specific spot, and that otherwise we have to retrain it again? Imagine if 100 epochs, you're going down like 5,000, right? And you ran it for a total of 10,000. And I was like, oh, that took like, a whole lot of time. It's like, well, not going to run it a whole lot of time again just to get to the same spot I had before. It seemed kind of backwards, right? Other thing too is like, what if we were right here and now we like are training forever and it's getting worse and worse and worse? Well, that stinks too, right? Because it's like we know, like we could actually check out the validation as it's happening and like, you know, watch those numbers go by and like stop it once it's done. But that's also a pain too. So we can do two things. So one is basically just say, hey, let's just keep every time the model gets better and better, let's go ahead and keep that model. So the idea here is that we would get, based on the validation curve, only keep the model that is essentially the best model for that validation. So we can actually use this thing called model checkpoint, which is built into Keras. And what this will do, basically, it'll save that model, like I said before, like saving a model, but it'll save the best model specifically for this fitting. So basically using this model.fit, so we have our model architecture and we're going to fit it on this training data for like say 100 or 1,000 or 10,000 epochs. It'll basically train it out there, but it'll go ahead and save that best model. So you can imagine it saving this very best one right here. Okay, and that way you can say, oh, cool, like, you know, you run it, let's say you run it, you forget it at night, it's like, all right, run it, don't worry about it. And you come back and you find basically your best model is saved right here. So that's really nice. I note that you can also change this, note that it's save best only is true. You can change that to false and it will save the best model as it happens. So let's say the next model is even better, next model is even better. So that way you can compare multiple models. So there's some ways, for example, you can actually go ahead and, if I look at this carefully, you can actually name the models different names. So for example, you can see here the file path is epoch. Like you can actually use this terminology right here and save the model for every so many epochs, so much validation loss and stuff like this. And you can actually save that for later and compare the models multiple times. So another useful thing, but in general, at least from like kind of like saying the saving the best model, you probably just use this guy, okay? So this is one way to do this. Another one is stopping early. Basically, it's like, hey, like let's say we find the best model, you know, and then the error is not either it's not improving very much or it's getting worse, right? Then you're just wasting a whole bunch of time, right? And you're like, I don't want it to run a whole bunch of time, like, you know, we're just waiting for something to happen. So this is something called early stopping. So early stopping can actually be done, or the early stopping callback can be done within Keras too. And basically it says, all right, go ahead and monitor a specific value. In this case, it's saying validation loss and say, okay, how much should it change for it to start counting how many times it hasn't changed? So for example, you've set this to 0, it means that the error is like the same exact error, you know, the next time. 0.1 says, okay, if it's within 0.1, we'll count that as it being the same validation loss, okay? And this patience equals 5 basically says, if it doesn't change within this tolerance, go ahead and stop it after 5 times. So you can imagine basically like if your error basically is like, let's say your loss is like 0.1, and the next time it's 0.101, and the next time it's 0.99, right? It hasn't really changed much. And it does that for 5 iterations of, hey, it's not learning anything anymore. Let's kill it right here and we'll stop training. So this is really useful again, because it means that you can make it stop. Basically, you can make sure that it's not wasting your time. Like if you got to this point, why train it for another 200 epochs if you know the error is going to keep going up? Okay. All right. Does that make sense to everyone? Cool. All right. Any questions about that? No. All right. So I strongly recommend doing something like this versus, I think the curriculum kind of mentions, it's like you can train it for 100 epochs, you know, or you train it for like 300 epochs, and then you say, oh, it didn't do very well over here. Let's stop it at 100 epochs and train it again. It just seems kind of counterproductive and kind of redundant. Okay. So this leads us to a couple of things about, like, okay, this is how we kind of find those spots where it is overfitting, right? Really stopping. But let's say we just like, hey, we want to try to avoid it from overfitting to begin with, right? Let's see, like, you know, if we can get it optimized as much as possible so it's not overfitting, right? So this is a good thing to have in conjunction with anything else, but you want to make sure your model doesn't get to that point. So one classic one is basically a regularization technique. So if you guys remember, we used L1 and L2 regularization for machine learning before, right? We used it for support vector machines. We used it for basically every machine learning algorithm we had L1, L2 regularization. Well, you can do the same thing basically for your neural networks, right? And the idea for regularization is that we have very large weights. We want to basically punish the model and say, hey, your weights are too large, you're way too confident, you need to chill out, right? So we're going to actually put in an extra punishment for just the fact of it being too confident. And that's really what L1 and L2 regularization does. So I won't go into details again, like the full like mathematics, but the main thing is you adjust your cost function. Remember that's labeled with J. we adjust our cost function by adding this extra term with lambda. And then this wi is our weights. So basically, if this weight is larger, it automatically punishes it, right? Because this j has to be as small as possible. So L1 regularization, which is like absolute value, it tends to put the vectors too close to 0, like really close to 0, where basically they disappear. And this is nice because it reduces the number of weights. We call this a sparse model. So the idea here is that you have very few, very few weights that are, or you have fewer weights than you started off with. So that way you can kind of like have a more compact model, okay? It's really also good for feature selections because it makes sure that if the weights are 0, it means that that feature is not important. So it's nice to basically use this to say, hey, you have a bunch of features and you're like, I don't know which features for it to use. You can actually use that to kind of reduce the number of features. Can be used kind of like essentially like dimension reduction without actually doing it yourself, okay? L2 regularization is basically the same idea as L1, but we have W squared. And basically this will tend to create more homogeneous, smaller weights. Won't reduce it to 0, but it'll make them smaller overall. And this tends to get better results. L2 regularization tends to be like the default that people will use for training. A quick kind of like note on like L1 versus L2 is that you can kind of see like why this happens is that L1 will prefer vectors like 1, 0, where L2 will prefer vectors like 0.5. So the easiest way for us to kind of look at this is just literally do the math. So pretend you have, for example, L1 and L2, okay? And we have our vectors, let's say 1 and 0, and then I'm just gonna do 0.5, 0.5, okay? And it's gonna basically do like, let's say we say, okay, oh, this is the bad way. I shouldn't have done it this way. Should have done like this, L1 and L2. Okay, so if L1 happens, we basically do 1 absolute value plus 0 absolute value gives us 1, right? L2 will basically do 1 squared plus 0 squared, which gives us 1. Okay, and remember we want the smallest thing. So let's try we do 0.5. So it's deciding between is it 0, 1, 0 or 0.5, 0.5. For L1, we get 0.5 absolute value plus 0.5 absolute value, which is just 0.5 plus 0.5, which gives us 1. Basically, L1's like, I don't care. Either one of these are fine. Like, I don't care which one you choose. L2, however, regularization will do 0.5 squared, which is 0.25. And then 0.5 squared is 0.25, which will give us 0.5. So you can see here is that for L2, this vector gave us the smaller value. So L2 will tend to prefer vectors that look similar versus things that have 1 and 0. So this kind of gives you a little bit of a sense of like why this is happening. It's just a mathematical property. Okay, cool. All right, and that is L1, L2 regularization. And then the last one is dropout. So tell you what, I'm actually gonna hold off to dropout till next time. And that way we have enough time. But know that dropout basically, it's kind of an interesting way to basically, you purposely try not to use parts of your neural network. And by doing that, you actually help the neural network get stronger overall versus like relying on one specific, like essentially pathway. So next time we'll talk about dropout. And that'll be like about 5-10 minutes at most. And then we'll talk about optimizations next time of saying how we can optimize our neural network to approach that solution faster. So I think these are kind of useful things for us to talk about because neural networks, again, are kind of like the building blocks to a lot of these other deep learning tools. So it's good to know, how you can optimize them, because if you understand how to optimize neural networks, it usually follows that you can do a better job optimizing other, more complex and nuanced networks. Okay. All right. So yeah, any questions? Cool. I'll stop recording here then.